Okay, so today I'm going to talk about the factors affecting the rate of reaction. There are certain factors that affect the rate of reaction. Basically, if we talk about the main factors that affect the reaction, there are only two. I'm going to write them here. The first is temperature, and the second one is the first one is temperature, and the second factor that involved, basically if we talk about it, we only consider the two. First is known as the second is concentration. So these are the two factors involved in it. First is reaction, second is temperature, second is concentration. So these are the two important factors in it, right? So let's discuss one by one each factor with its explanation. So let's just delete it. These are the two factors that we need to discuss in detail, right? So the first factor is nature of reactant. Nature of reactant. Now what does it mean? It means that nature of reactant refers to that whether the rate of reaction is fast or slow and what exactly the nature of it, right? So let's just do it. Let me just reduce the size, and yeah, okay. Some reactions are fast, some reactions are fast that they occur in instant of time, in instant, while others are too slow. While others are too slow, too slow that they take way too long to get done. Then that they take a way too long to get done. Let's see the examples here. If you can see here, I have taken the two examples that can easily some more support my statements I have given here. Rusting of the iron. You know that the rusting of a tiny iron takes many years. This reaction cannot be done in one day. For example, take a nail and put it in the place where it is directly contact with the surface, with the air, if possible. You'll see the rusting after a way too long, right? For example, it takes approximately 2 months or 3 months or 4 months because it takes time. If we talk about the sugar, if if you have a temperature, if you want to dissolve this sugar in the water, the most appropriate way is that you can take a hot I'm sorry, hot milk, and you can add this sugar into this water, into this milk, which gets dissolved in it in an instant of time. So this is a very fast reaction, and this is a very slow reaction. You cannot determine their rate of reaction. Although if we talk about the one more reaction here, let's just discuss it. For example, NaCl, NaCl plus AgNO3. Then it turns into, after the reaction, it becomes AgNaNO3, which means sodium nitrate and silver chloride. So sodium nitrate NaGCl. This is basically a reaction. It is a very fast reaction. Just why is it fast? Let me just tell you this thing again. Yeah, I've told you this in the previous video. As you can see here, if I just want to highlight it, it's already present in the form of ions. It is positive, it's negative, it's again positive, it's negative. I'm not writing the oxidation state. Positive and negative, positive, and so on. So they're already present in iron. They do not take time to break their bond to make with each other. So already present. But of course, ammonia N2 plus H2. I'm not balancing the equation that you can do by yourself. H2 is equals to NH3. This is basically intermediate reaction where you can determine the rate of reaction because it takes time. This is something like this. Let me show you. This is nitrogen with double bond, hydrogen with single bond. It takes time to break the bond and to create an ammonia which has one lone pair, right? So yeah, it takes time. The process takes time. So we need to. So some reactions are reactions that are fast that occur in an instant, while other reactions are too slow that they take a way too long to get done. Yeah, so we are done with the definition. rate of reaction. You can see the example here, adding the sugar into the milk, it takes time to get dissolved into it, while taking the rusting of iron takes a way too long to get done. So its rate of reaction is so fast and furious. Right. So let's discuss the next rate of reaction, which is let me just read it. Is basically rate of reaction. Rate of reaction. Let's take another mark. So it's just given here. Rate of reaction is directly proportional. Actually, rate of reaction is inversely proportional to the stability. Stability, I'm only writing Sn dot T, stability of the reactant, which is R. I'm going to ST, I mean stability of reactant, and it is directly proportional to the stability of the product. And R, sorry, ROR ROR directly proportional to the stability of the product. Stability of the reactant and stability of the product. What does it mean? It is pretty obvious. Stability of product, pretty obvious that when the reactant gets, this is we have discussed the graph as well. The reactants, the amount of the reactant reduces but the amount of the product increases. I have discussed it in the previous video. So this is same, the rate of reaction. If we have an unstable rate of reaction with the reactant, of course it breaks down and it performs reaction, it turns into product. So product is a stable. Then we can include example as well. For example, let's see that these two we don't need to discuss it. For example, we have a reaction of acetic acid, that's vinegar that we usually, we all know, present in our kitchen, used for the cooking purpose in different foods, just to add the sour taste in it. CH3COOH. Actually, CH3 is a bulk molecule. When it breaks down, its reaction is something like this. This is H. My god, I need a dark marker for explaining. This is something like this. CH3 CO O and then plus hydrogen. Hydrogen is something like this. This is the reaction, hydrogen. And on the other hand, we have HCOH, which is formic acid. This reaction is something like this. HCOOH. Here we are talking about the stability of the product. So this is HCOO negative plus OH. Right? So this is the reaction given here. As you can see that this is the bulk molecule and it provides a positive charge, here it gets a negative charge, so it's highly unstable. This one is highly unstable. This is highly unstable. Unstable. I don't have dark marker to explain it, but I guess it's just prominent. It is unstable while this is stable. So rate of reaction stable. This is stable. So rate of reaction here is stable, while there it is unstable. This is a stable rate of reaction, right? So let's just proceed further and let's just delete it and discuss the next thing. We need to delete the pictures as well. Surface area. Let's take example of surface area. For example, the rate of reaction also depend upon the surface area. Okay, let's just erase it. So rate of reaction also depend upon the surface area. For example, let's take sugar cubes. Surface area of sugar cubes. Okay. The rate of reaction is directly proportional actually to surface area. The rate of reaction ROR, the surface area, the surface area, the surface area. The higher the surface area, the more surface it has to perform the reaction. Surface area. Surface area. As you can look here, surface area is less. If you to consider this complete cube, as you can see here, the surface area is large, but the most of the surface area is hidden inside the layer, which means it takes a time to dissolve into this solution, and then all the area inside there will be visible. But if you talk about this cube as compared to this cube, it has a large surface area, just because as you can see here, it's smaller inside, and usually it instantly get dissolved into the solution. So surface area also matters if you talk about the reaction. Surface area matters as well, right? So let's just go ahead. Here also surface, looking at the surface area. Here look at the surface area. Compare this complete as a complete cube, and then compare it to the surface area. So it also matters. The larger the surface area, don't consider that it has large surface area, which means can perform more reaction. No, the most of the layer is hidden inside it, right? But when it get dissolved into the solution, for example, this is a container, it get dissolved into it, takes a time to dissolve the upper layer, then the other layer get dissolved. But if you talk about this cube is very small. You can easily consider, for example, take a sugar powder and then take a cube of sugar. As you can see that the cube of sugar takes a time to dissolve in the water, while the powder sugar takes a very instant of time to get dissolved into the water. So which has lots of area? Of course, the water of the sugar has lots of area. Don't consider that it's powdery surface and does not have surface area. It doesn't have surface area, right? So this is basically that you need to keep in your mind while doing this sort of